Hi, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Today we're going to be talking about the Big Bang and specifically redshift. Last time we looked at Edwin Hubble's amazing discoveries about the nearby galaxies, and we're going to extend that into his discovery of the cosmological redshift distance relationship. The cosmological redshift is one of the key pillars of Big Bang and the cosmology itself. It demonstrates, just let the cat out of the bag, that the universe is expanding. We're going to look at the evidence for the redshift and why we treat that evidence as supporting the expanding universe. Once again, cosmology is the study of the entire universe and everything in it and what it's going to do, how it moves, its origin, and its fate. Next, we're going to utilize an incredibly important idea that is the cornerstone of the entire study of astronomy, the cosmological principle. The cosmological principle states that on the largest cosmic scales, the universe is both homogeneous and isotropic. This means there's nothing special about our location in the universe other than the fact that it's where home is. Homogeneity means that the distribution of things is smooth and regular. There can be an overall pattern, but it must be continuous and unchanging in space. So a brick wall, perfectly laid out, is homogeneous in this regard. It's all brick, and the individual bricks are arranged and stacked in roughly the same way, and they all have roughly the same size, or range of sizes. Isotropy means that everything is observed to be roughly the same in every direction. In the brick example, if you're right up next to the brick wall looking around its surface, because of how the mortar is laid out between the bricks, there are different kinds of views in different directions. They might seem to repeat, so not every angle of direction looks the same. Isotropy takes this further, stating that there is no preferred direction in the universe. That is, from your current location, no matter which direction you look, the universe will look the same. In our brick example, this would only work if the wall were one big brick with no mortar between the bricks. For the universe, if you take a big enough sample, you see roughly the same numbers, sizes, and counts of galaxies in each direction. That's isotropy. We say that the universe is isotropic around any point in the universe, and of course, in particular, around us, which is supported by the observation. Homogeneity means that there's no preferred location in the universe. That is, no matter where you are in the universe, if you look at the universe, it will look roughly the same right around you and be made of roughly the same things. However, redshift results from the recent redshift surveys, such as the Sloan Digital Sky Survey on the right and the 2DF Redshift Survey on the left, of the distribution of relatively nearby galaxies seem to imply that the universe isn't homogeneous and isotropic. In other words, the galaxies in one direction are not seemingly distributed in exactly the same way as galaxies in another direction. But the galaxies that are investigated in these two surveys only extend out to a redshift about 0.2, which is equivalent to a distance of only 750 megaparsecs, million parsecs. We'll get to that redshift, what that means soon. When we study the most distant objects, we find that at much larger distances from the Earth, the structure appears to smooth out and become more homogeneous on the largest size scales. For example, all sky surveys of the positions on the sky of objects detected by radio telescopes reveal a much more uniform appearance. The objects seen in radio surveys are mostly expected to lie at higher redshifts than the galaxies seen in optical light, as shown here. This suggests that when we consider the largest distance scales, the universe appears to be homogeneous and isotropic. Thus, we currently find support for the cosmological principle in the distribution of galaxies in the universe. Furthermore, if you combine the observational evidence for homogeneity on the largest size scales with the argument, or even assumption, that the laws of physics are the same everywhere, implying there's nothing special about what's going on where we are or anywhere else, then isotropy as seen at one location means isotropy at all locations in the universe. If you have a homogeneous universe, from physical law arguments or radio galaxy surveys, and you have isotropy about one point, i.e. our home, then you have isotropy everywhere. Net-net, the universe looks the same everywhere and is made of the same stuff, then no matter where you are, you're going to see almost exactly the same things. This, of course, doesn't apply to time. Things do look different long ago than they do today. This is very important, and I'll use this observationally supported idea to make an astounding claim at the end of this video. In a previous video, I talked about the great distance debate in the early part of the 20th century. It was solved by Hubble in 1929 when he determined the distance between the Milky Way and the Andromeda Galaxy. as well as the distances to some other spiral nebulae, which is what they were called at the time. Let's do a quick review of a couple of galaxies, M81 and M82. M81 is the spiral on the left, and M82 is the smudge on the right with the little red bits going through it. Before 1929, nobody knew how far away these nebulae were. All such galaxies were thought to be star-forming regions or planetary-forming regions, or something like that, or perhaps even just big clouds of swirling disrupted gas. When looking at the images taken at the time, the confusion is easily forgivable. An image like this, which was taken with a modern backyard observatory by Johannes Schedler in Austria, demonstrates a huge amount of detail. Back in the 1920s, astronomical imaging was in its infancy. Today, we know these are a pair of interacting galaxies about 12 million light-years away, each composed of about 100 billion stars. It all begs an important question. How exactly do we know the distance to these galaxies? What put the great distance debate to bed and finally showed us once and for all that these spiral nebulae were in fact well outside the Milky Way? In other words, it's all very pretty and all that, but how do you know how far away they are? Between 1912 and 1917, prior to Hubble's discovery, Slipher at the Lowell Observatory was able to measure the spectra of about 25 of these spiral nebulae. These spectra were used to get radial velocities for these 25 galaxies. 21 of them showed a redshift with some high speeds as up to 1,000 kilometers per second. This redshift, if interpreted as a Doppler shift, showed that galaxies are rapidly receding. His paper discusses this process and the difficulties, and I put some edges at the top. And right in the middle there, that's the table of his galaxy measurements as published in April of 1917. However, he didn't have distances to these things, these nebulae, but he knew he was onto something very important. It was just that he didn't make the cosmological connection to the distance. Unfortunately for him, Lowell Observatory had no way of imaging the galaxies in enough detail over long enough periods to begin to do any kind of distance measurements. And he stated this unequivocally, saying, "This is the so-called island universe theory, which regards our stellar system and the Milky Way as a great spiral nebula from which we see within. This theory, it seems to me, gains favor in the present observations. It is beyond the scope of this paper to discuss the different theories of the spiral nebulae in the face of these and other observed facts." He just didn't have the information on distance in order to continue this, and this was his concluding paragraph. Then, in 1929, Edwin Hubble, who you see pictured here, finally measured the distances to a few galaxies, including M31, the Andromeda Galaxy, M33, and other local group galaxies. He did so using what's known as a standard candle, or something that has a known luminosity, or energy output. If you measure the brightness of something at some distance for which you know the luminosity, then find another of the same thing, but the second one is farther away, then it'll be dimmed by the distance squared. Hubble set out to compare the distances with the recession velocities, and subsequently found that the recession velocity is larger if the galaxy is positioned further away. This was understood after much debate to mean that he had found the systematic expansion of the universe. This is a really big discovery. In fact, it's one of the most important discoveries of 20th century science. It changed the nature of the study of the universe. It was the beginning of our journey away from learning about the story of the origin of the universe from stories told in ancient books to cosmology being a precision science. And that's where we are today, almost 100 years later. How far is the Andromeda Galaxy from the Milky Way? That was the question of the 1920s. How did Edwin Hubble accomplish this feat, and what were his standard candles? There were the Cepheid variables, whose light curves have been extensively studied by Henrietta Swan Leavitt. Leavitt studied variable stars of the small and large Magellanic Clouds as recorded on photographic plates taken with the Bruce astrograph at the Boyden Station at the Harvard Observatory in Peru. She identified over 1,700 variable stars. In 1908, Leavitt published the results of her studies in the Astronomical Observatory Annals at Harvard College, noting that the brighter variables had a longer period of variation. In a 1912 paper, Leavitt examined the relationship between the periods and the brightnesses of a sample of 25 of the Cepheids variables in the Small Magellanic Cloud. She determined conclusively that there is a simple relation between the brightness of the Cepheid variables and their periods. We discriminate between all the various kinds of variable stars by looking at how they get bright and dim with time. Cepheids, first, are extraordinarily luminous stars. Second, their light curves have this distinct shape with periods of oscillation on the order of tens of days. Cepheid variable stars can get you the distance to an object in which they live. Now we just need a good handle on the redshift. These peaks follow an important pattern. Most importantly, Leavitt found that the luminosity at the peak brightness is tightly correlated to the time between successive peaks. Therefore, if you can find some bright stars and hope they aren't one-off novae, then you can return night after night to get the period of brightness of variation. Once you've determined that period, then you know the absolute magnitude of the star at the peak brightness. Once you know that, you compare it to its apparent magnitude and use the distance modulus equation, which I described at length in the previous videos in the series, to get the star's distance. But basically, if the Cepheid happens to live in a distant galaxy, then comparing nearby Cepheids' brightnesses with the distant ones will give you the distance. So Hubble's plan was to look for Cepheids in M31 and other galaxies and use the Leavitt period-luminosity relationship from the Milky Way Cepheids to get the job done. Luckily, these stars are so bright they can be picked out in the relatively nearby M31 and the Andromeda Galaxy. So Hubble went off to find those stars by taking photographic plate images of M31 and M33 and was rewarded with a bunch of candidates, as we can see from this photographic plate of M31 from October of 1923. Edwin Hubble first spied the star on a 45-minute-long exposure he'd taken early on October 6, 1923 with Mount Wilson's 100-inch telescope. Hubble had spent months trying to determine the distance to M31 to see if it and other such controversial spiral nebulae were distant parts of the Milky Way or instead distinct, quote, island universes. He'd initially marked the three stars on this plate with N, thinking they were novae, but when he compared his plate to earlier exposures, he realized that one of the three was actually variable, so he crossed out the N and excitedly pinned, quite clearly, var next to it. Here's another one of his plates for the galaxy M33, another nearby galaxy, which is really just the big smudge in the middle from 1926, as published in the Astrophysical Journal. You can see how he marked up a series of Cepheid variable stars for observation and follow-up. Notice that this plate is negative, as is a common convention for publishing results, so the stars look black and the sky looks white, and the galaxy is that big cloudy fuzzy thing in the middle. Numerous follow-up observations revealed the periods of these Cepheid variables. Each dot on this curve represents a separate 45-minute exposure of that galaxy. A light curve was fitted to the observations. Likely, each of the four candidates that you see here was observed on the same photographic plate on the same run. But things can go wrong with such photography, and these light curves are folded to stack onto the light curve. It's not like they began measuring before day zero and it's only 2 peaks. It's many, many, many days, and this is convoluted and folded to find this pattern. You can see in the sawtooth patterns of these 4 variables, which are indicative of Cepheid variability. Hubble then went on to make these radial velocity measurements. He did this for a number of galaxies, using the same processes that Vesto Slipher used. However, he used the 100-inch telescope on Mount Wilson, which was the most important telescope of its time, just like the Hubble Space Telescope and James Webb Space Telescope are today. Incidentally, Hubble's observing partner, Milton Humason, was actually one of the mule drivers who helped bring the 100-inch mirror all the way up Mount Wilson in California. He'd dropped out of school and had no formal education past the age of 14, and he loved those mountains and found a job taking materials and equipment up to the mountain while Mount Wilson Observatory was being built. In 1917, he became a janitor at the observatory, and just because he really loved it, he volunteered to be a night assistant at the observatory. His technical skills while doing the work were rewarded by George Hale, who was the director of the observatory, who hired him onto the staff in 1919. Humason then became one of the greatest observational astronomers of the time. He and Hubble would stay up all night with the telescope, taking the spectra of these distant objects. Getting just one spectrum would take between 30 and 50 hours of exposure to collect enough light to find the spectrum. This meant that the same photographic spectral plate had to be taken out of the telescope every night at the end of the session and put back into the telescope before starting. This would be done over many nights to build up enough exposure to catch the faint light from these gargantuanly distant objects. To make this process even more painstaking, the galaxy would have to be centered in the telescope. The telescope did have tracking, but it wasn't sufficient for their needs. Thomson and Hubble continuously peered through a centering eyepiece at the base of the telescope to ensure that the tracking was perfect. This extraordinary process took a very long time to create the data that you see on this image. For reference, the top one, NGC 221, is a satellite elliptical galaxy of M31, the Andromeda Galaxy. NGC 4473 is an elliptical galaxy located about 50 million light-years away to the constellation Coma Berenices. NGC 379 is a lenticular galaxy in the constellation Pisces. His quote of 7 megaparsecs from the second one, or 7 million light-years, is off from today's reckoning. His distance measurement put all these as too close compared to modern measurements. But that's not really the point. The point was, at the time, these were just being discovered to be outside of the Milky Way. And this is what the whole cosmic distance debate was all about, which I discovered in a previous video. Now let's look more closely at just one of those observations so that we understand what's going on and what we're looking at. We have a series of lines, and we're going to call them the calcium H and K lines. These are the tiny dark spots in the middle of the smudge, in the middle of the image, surrounded by a red circle. I've also lined them up with a red arrow going up to lambda naught. And that's what I'm calling the calcium H and K line. There's also 2 yellow arrows which indicate reference spectra. The reference spectra was probably going to be something like a such as a reference lamp, like maybe iron carbide, vaporous iron carbide, a very hot iron carbide thing which is vaporized, which then glows and emits this very particular light. The galaxy spectrum is in purple and is the smudge. That's the real data. The things on the left and the right are references such that you can actually make a measurement of the wavelength. The reference lamp is a known wavelength set because you know the elements, carbon, iron carbide, or whatever they were using, and put that down and say this is the wavelength of those light. And then you put the spectrum in between it of the galaxy. And then you check again. If you look at calcium and look absorption of calcium, and you have a list of lines, a list of spectra, including vaporized calcium, you find in a table that there are wavelengths according to which have been named H and K in terms of calcium. That's what their names are. It's just a list in a book saying, oh, if we vaporize calcium and heat it up, we get a whole series of lines, and one of them we call H and the other one we call K, and they're very prominent. And the little red circle shows them. But the reference lines show that they have been displaced from their rest wavelength. And the rest wavelength is that lambda sub E. Lambda sub E is where they would be naturally in the laboratory, and I've indicated with a blue line where that should be. And the little white arrow shows how far off to the right, or to the red, these wavelengths of light have been displaced. So that's really interesting, and we'll continue on a bit. We'll talk more about that later and how that comes about. So all these galaxies were used, or at least their spectra can be best measured because of that strong absorption feature, or to K and H in these things as well. They're all the same process. Something is doing K and H absorption. The purple line crossing all the spectrum marks the rest and lab wavelengths for the calcium H and K lines. Galaxy spectra like these are typically characterized by a strong continuum component, which is the smudge going across the middle, not the reference little tick things. This is caused by a combination of a range of stars spanning a range of temperature. They all combine together in that galaxy's light to form one spectrum, which is fairly flat overall. The H and K absorption lines are superimposed on top of this spectrum. on top of this continuous spectrum, and are due to the absorption of atoms, which are called metals in astronomy speak, and molecules in the atmospheres of stars, and to cold interstellar gas clouds that siphon off the radiation at these specific frequencies. This implies that there's a presence of old stellar populations, which are typically found in elliptical galaxies and in the bulges of spiral galaxies. We understand that these kinds of galaxies have the same kinds of stars that the Milky Way does, and the absorption features are therefore due to the same kinds of processes that we see locally and in the laboratory. And they're not different processes that act on different wavelengths. Therefore, the absorption features that are seen in these images are redshifted, and the redshift is the red arrow pointing to the right, and the resultant location of the H and K lines is inside each of those circles. Again, we're using the cosmological principle to state that there's nothing special going on anywhere, so that the H and K lines are formed at the same wavelengths in the same kinds of stars and the same kinds of nebulae. And also, if we're looking at the galaxy's shape, we see that the farther they are, the smaller they appear to be. This shape difference, assuming they're roughly the same size, combined with the distance measurements, seem to indicate that the radial velocities do increase the farther away the galaxy is located. Now let's rotate this little diagram to help us understand even better. The spectra that were taken by Hubble look to be in black and white. Sometimes it's helpful to remember that the spectra are seen by us in bright light to be a rainbow spectrum. Now if the top spectrum is stationary, and the bottom one is rushing away from us extremely fast. And then when we measure the rushing one, we find that the lines are displaced from their laboratory wavelength to longer and redder wavelengths. This is called redshift. Okay, so let's take a moment to reflect that this didn't have to be this way. We can make up all sorts of fancy ideas, science fiction, pure speculation, wild word strings based on a jargon generator. Nature could have surprised us in a lot of ways. This surprise is a doozy. It was a shocking discovery that nearly every galaxy is rushing away from us. 1. Redshift is an observational discovery. It is nearly universal across all galaxies. It didn't have to be this way. This was a discovery. And 4th, this was extremely important. We'll now look at Hubble's law and show how it arises from the relativistic theory. First, let's define the idea of redshift. Redshift, Z, is a unitless measure of distance, is a unitless measure of the difference between the observed wavelength of light and the emitted wavelength of light divided by the emitted wavelength. Basically, a measure of how much the light has been stretched or compressed from its original emitted wavelength. Now we've rearranged the equation to help us with some things later. Again, the redshift Z is the ratio of the change in the wavelength of a moving source compared to its wavelength at rest. This isn't observable. We just have to know the wavelength of the light when it's emitted. That's why we really depend on the physical laws being the same everywhere in the universe. If it's not moving away, then the redshift is defined to be 0. So now I've added some physics. On the right is the special relativistic formula for the Doppler shift due to the emitter and observer being in relative motion towards or away from each other. Doppler shifts are more familiar when car speeds by you with a blaring siren. The pitch goes higher as it approaches and it goes lower as it goes away. This formula takes into account the first postulate of special relativity that the speed of light is always the same for all observers. To get more about that, please go and watch my series on special and general relativity. Suffice it for now that the big square root is the fully relativistic way of writing the Doppler shift. Again, this is experimentally verified, as well as originating from a general theoretical principle. The rest wavelength, meaning what we would measure if the thing emitting the light were just sitting there, of something emitting a pretty shade of green at 5500 angstroms, is given by that lambda sub emit. Lambda sub obs means the observed wavelength, with v meaning the speed of recession or approach of the source emitter to the observer, and c is the speed of the wave, here, the speed of light. This formula applies to all sources moving with respect to any receiver when we're talking about light. Let's make things easier on ourselves and note that all the reference spectra we looked at before were speeding away at speeds much less than the speed of light. This is helpful, not just in the math, but in helping you understand it. So that big square root can be approximated by a much simpler version. So now we see the relationship between redshift and the recession speed for slow speeds. But it looks like a mess. If you look at both ends, we see that we can reduce this down even more. And now we have the final form for our relationship. We haven't removed the wavelength observations. They are represented by the Z. Now when Hubble and Humason did their measurements, they assumed it was a Doppler shift and got that Z. Now with both of these measurements, a distance from the Cepheids and a recession speed from the redshift, Hubble plotted his data and discovered this relationship for all of these galaxies. This is Hubble's actual data from 1929. From it, he derived a best fit value for the relationship, which looks like the solid line. The slope of that line that Hubble derived was 500 kilometers per megaparsec, which is much larger than the values understood today. So that's it. Hubble's law directly relates two observable measurements, one from radial velocities in the spectra and another by understanding stellar physics and knowing various standard candles. Combining these two things together, you can measure the distance to some unknown galaxy by getting a radial velocity alone. Oftentimes, it's very hard to pick out a Cepheid in a distant galaxy or wait for a supernova, but spectra are easier to measure. Therefore, it's important to discover more standard candles and get finer and more precise radial velocities. Arguably, the second thing is the easier of the two. Our faith in the fact that the physical laws of the universe are the same everywhere leads us to trust this distance-redshift relationship as real. The main result is that the more distant a galaxy is, the faster its recession velocity. Hubble's original value of 500 kilometers per second per megaparsec is a lot bigger than we know it is to be today, but that was due to some calibration errors in his work. Those errors don't invalidate the conclusion, only the rate of expansion. You'll often see h sub naught called the Hubble constant, but it's really not. The Hubble constant is the value of the slope of that line at the present cosmic time. In the past it was different, and it will be different in the future, so its best name is the Hubble parameter. H naught is measured today to be about 72 kilometers per second per megaparsec, and if we measure with most standard candles. However, it's 68 if you derive it from cosmic microwave background measurements. More on that later. The obvious goal is to then obtain distances to galaxies. To indicate our attention, let's invert this equation to obtain the distance as a function of redshift for relatively nearby galaxies. Here again, z is the cosmological redshift, z is the speed of light. It gets more complicated for extreme distances and look-back times, as we saw with the original Doppler formulation a few slides back. H naught also measures the expansion rate of the universe. We'll show you why it does that shortly. But to progress the story for skeptics, in 1931, Hubble and Humason followed up with measurements of farther galaxies and groups of galaxies. The relationship held for much more distant objects. These observations are what finally ended the great distance debate about the size of the universe. It was no longer just the Milky Way. It was the Milky Way plus lots of other things that seemed to be the Milky Way at very great distances. This was a hot topic of debate prior to Hubble's work, whether the universe was just the Milky Way or if there was anything beyond. I did a long video on this amazing part of science history, and you should go check it out. Note that their data was from just 2 years prior, makes up only the tiny corner of the newer data. And this was just the beginning. Here's a Hubble diagram from 2004 that shows the relation up to about 650 megaparsecs. The standard candles here are type 1a supernovae and were derived and measured by Robert Kushner at the Harvard-Smithsonian Center for Astrophysics. They were critical in letting us know that the Hubble parameter has changed with time. These specific type of standard candles. More on that in my video on dark energy and cosmology. The slope of this line is roughly 72 kilometers per second per megaparsec. Way down in the lower left-hand corner marks the span of Hubble's original diagram from 1929. It doesn't matter which standard candle you use. We always measure the same distance-velocity relation. All of these are direct measurements with the distance and radial velocity, each with different standard candles. There is a rub though. Indirect measurements of the Hubble parameter using the cosmic microwave background and baryon acoustic oscillations give a significantly different answer, which I'll talk about later. The Hubble Key project was one of the first to do a major search for many Cepheids in distant galaxies, and then measure the Hubble parameter. They gave their final work in 2001. In fact, this project was one of the core reasons for the launch of the Hubble Space Telescope and why the orbiting observatory was named after Hubble. Just to make sure we all know, there's no one on board the HST. It's a robotic facility. On other recent measurements, as shown here using Cepheids and other standard candles, show that H0 is about 72 or 73 kilometers per second per megaparsec. H0 is very hard to measure. Recession speeds are roughly easy to measure from the shifts of spectral lines, but distances are very hard. And the recession speeds are complicated by the random motions of galaxies due to the being in clusters or falling towards 100 megaparsec scale mass gradients. These extra non-cosmological motions have to be taken into account. However, subsequent measurements using Hubble Space Telescope and now the James Webb Space Telescope support these measurements. The accuracy, precision, and interpretation of these observations are not under question. The universe is expanding. So all these projects to measure the Hubble parameter have the intent of being able to faithfully represent the distance to some new or unknown galaxy using only the redshift as measured strictly from the spectrum. Nearly every astrophysical process that we want to learn about depends on us accurately knowing the energy output. If we know the distance to something, then we can quickly relate how bright the object appears to be to how bright it actually is, that is, its energy output. Once we know that, we can relate processes evident from its spectrum, from its environment, or from its appearance to teach us what's going on over there. So without the Hubble law, we wouldn't have a handle on a lot of what's going on. But first, let's get back to that expansion of the universe stuff. Incidentally, the inverse of the current value of the Hubble parameter gives us a rough approximation for the age of the universe, because the units are kilometers per second per megaparsec, and if we know how many kilometers there are in a megaparsec and how many seconds there are in a year, then we can get a good guess. Okay, so let's go through it real quick. First, we take this thing and put the seconds and megaparsecs on the top because that's what the per and per allow us to do, and I'm going to kind of use this as a mega fraction and start canceling units. Next, we want to try to get rid of the megaparsecs as a thing and convert them to kilometers. So first we know that 1 megaparsec has over, 206 trillion, not trillion, billion, well I guess you get trillion if you're talking Brit talk, but 206 billion astronomical units. But how many astronomical units are there in a kilometer, or reverse-wise, how many kilometers are there in an astronomical unit? There's about 150 million kilometers in an astronomical unit. And finally, we've converted now megaparsecs to astronomical units and astronomical units to kilometers. We got kilometers on top and kilometers on bottom, but we have seconds on top. The age of the universe in seconds isn't really good. So in 1 year, there are just over pi million, 10 pi times 10 to the 7th seconds in a year, which is a really cool little statement. It's a little bit over pi. So we can call it almost 32 million seconds in a year. And if we multiply all across the numbers across the top and multiply the ones at the bottom and then divide up and down and get rid of the units, we're left with years. And that's approximately 14 billion years. So that's a rough, good guess as to the current age of the universe, which is an interesting thought about what you get from just this rate of expansion. Hubble's law demonstrates that the universe is expanding in this systematic way. The further a galaxy away is from us, the faster it appears to be moving from us. The Hubble parameter, H0, is a measurement of the rate of expansion of the universe as measured at the current cosmic time. It is not a distance velocity centered only on us. It's not just that. How do we know it's actually expanding? Let's actually go through what we mean by the expansion of space and how that relates to Hubble's law. And we're going to drive this using geometry. Distance measurements are always measured some length, so it doesn't matter how that length is measured. So what I'm going to do is I'm going to make, say, a really big triangle somewhere in the universe. I'm also going to say that it's anywhere, and it's any rotation or orientation that we can imagine. We can rotate it around any which way and put that triangle in any location in the universe. Let's start with the triangle being around when the universe was, say, small. And I'm going to color that triangle purple. I've labeled each side and each vertex of the triangle. My hope was to kind of make it look like we're going around the triangle. R12 at T0 means the length of the side of the triangle between vertex 1 and vertex 2. The T0 means the starting time. We use parentheses on each because that length is a function of time, and we're marking the starting point. Now at some later time t, the triangle has grown such that all the angles are the same with respect to each other, and the length of each side has doubled. Superimposing the two triangles, we can see that it's just a bigger but looks the same. If you remember your high school geometry, we used the angle, angle, angle test to show that the two triangles are similar but not congruent. This just means they look the same but differ only in size. Now let's capture the time functionality of the change of the sides of the triangle. Whatever happened, to maintain its shape, all the sides grew in exactly the same way, meaning the scale factor function was the same for all three sides. I'll call that scale factor a as a function of t, or a of t. We don't know the functional form of a of t. It could be a wild function of time, or very simple. It just applies to all sides equally. So now, let's go through and peel each one of these things and pull them up to their respective places in the equation. And I've captured and related all the sides as a function of the scale factor. In each case, the r of t naught is a constant, each of those three on the right-hand side. The size varies due to the scale factor function, a of t, and on the left-hand side is the resultant size after some time t. We'll just make it clean up so we have a little lined up so we're not looking at things that are moving around. Looking at all three equations, these could be vector equations, explicitly demonstrating the orientation and location in space. However, we posited that the starting triangle's orientation and location were arbitrary. This is actually a restatement of the cosmological principle. Now let's just take a look at one of those sides. Any one will do, since this whole thing was arbitrarily chosen. And we now see how this equation changes with time. We want to get that function. We must have varied somehow, small to big. So now we're going to check that. And we're going to first sometimes use convenience of the dot notation, which shows that a dot above a variable means a time derivative. So that d dt means a derivative with respect to time, and a dot is just a very shorthand notation way of doing that, so you don't have to carry around all that writing. Next, we use the definition of speed as the rate of change of distance to rewrite v sub 1, 2t as v of 1, 2. I'm going to use v for its speed, not s, since strictly speaking this is a velocity, which attaches a direction. But I don't really care about the direction of the change at this point. Now then, we're going to plug that top equation into the bottom one by noting that the r12t naught is equal to the r as a function of time divided by the scale factor at that time. And therefore, we have all the variables as functions of time in one equation. But now we want to simplify our notation for clarity even more. Since 1 to 2 was arbitrary, we don't even need that subscript, and the time variable is a given for everything, same with all the rest. Finally, we're going to call r sub 1, 2 d for distance. Then we get something that looks like this, a blindingly simple looking thing. But wait, what's that a dot over a thing? That's kind of familiar. It's actually the Hubble relationship, where we define the Hubble parameter as the change in the scale factor divided by the scale factor. H naught is just its present value at the present time. That's why I called it parameter and not a constant. This is the Hubble relationship. And now all we need is to understand how Redshift measures and encapsulates that scale factor A. Okay, so it's worth stopping here for a moment. I was a bit sneaky and glossed over everything related to distances. As you can see, the sides of the triangles are lengths, but more importantly, they are lengths at one exact moment in cosmic time. This, in general relativity, is called a proper distance. At t sub 0, and at a later time t, we've, quote, stopped time to take a measurement of each side. That length is called a space-time interval. This whole idea is assumed the cosmological principle, isotropy and homogeneity, for how we set up the triangle in our space. Then we said that the triangle expanded in that space. However, what if space itself expanded? Why would we ask such a question? Because when general relativity was being formulated, it was in response to the question, how does gravity work within the framework of special relativity? If we can make measurements nearly instantaneously, or at least seemingly so compared to the size of the thing measured, then we can use the old Pythagorean theorem to get the lengths of the sides. Time doesn't figure into that, but special relativity asks, what if you measure lengths when something's moving fast, and you posit that c, the speed of light, is a constant? Then you get a link between time and space. But why expansion? Why? Back in 1900s and 1910s, when Einstein first developed special relativity and general relativity, it was well understood that gravity attracts. It was also known that the Earth was very old, as are the Sun and Moon. So for stars and nebulae to not be crashing down onto each other when they're so big and so massive, yet relatively close enough to each other that it seemed worrisome that they hadn't crashed into each other and made one big blobby ball of stuff. To alleviate that worry, imaginative mathematics were developed, quite apart from the questions of the astronomers and the physicists. These solutions to the Einstein field equations of general relativity tried to keep the heavens from crashing down on us. If space expanded, that would do the trick. So I've essentially followed the mathematical argument by simply creating a spacetime that expanded. I've also used the ideas of homogeneity and isotropy to show that this triangle growth would happen anywhere. H0 would just simply be that rate of growth. In some sense, this is completely physics-free. What we now need is a method to actually measure the lengths of these triangles, especially when the sides are very, very, very large. So let's look at our only hope, light. Let's presume in the previous discussion is true. What does that tell us about light? So if we start with a galaxy emitting light on the left, and then we watch what happens as the universe expands. And the light has finally arrived at the telescope. So now we have a thing moving in space-time. According to normal physics thinkers, if a thing moves, it has momentum. That's a basic Newtonian mechanics. If a particle accelerates anyway, it changes momentum. But light doesn't ever change its speed, and its momentum has been experimentally verified to be dependent upon its wavelength, and the h is the Planck's constant. Trajectories in spacetime are called geodesics, and they are the curved spacetime idea of a straight line. These straight lines also must take into account the passage of time. Light's geodesic is called null. I discussed this at length in my lectures on relativity, so I won't expand here. Combining the null geodesic, a statement of physics about the nature of light always going at c for all observers, with the concept of light as a particle with momentum inversely proportional to its wavelength, we get a startling result. Light changes wavelength as it passes through a changing spacetime because it cannot respond to that change by slowing down or speeding up. No process is operating on the light other than traveling through space. So to continue traveling along the geodesic, it can only change one thing, its wavelength. Again, a null geodesic is simply the shortest zero-valued spacetime interval. In other words, it's what we would call a straight line in a curved spacetime if you moved at the speed of light. There's a lot that goes into this statement, really, and you spend a good deal of time in a general relativity class learning about parallel transporting in a vector in and on a curved manifold, specifically to the form of the Friedmann-Robertson-Walker metric as you propagate a photon along a null geodesic. Its momentum along this path varies like the energy of the photon. So let's see how this plays out. We return to the redshift definition and see how that scale factor comes into play. We rewrite it for clarity. And now we apply the scale factor to each of the wavelengths of the photon, noting the observed wavelength is just the scale factor times the original emitted wavelength. Okay, we can do this because light travels on a null geodesic and its energy is directly proportional to its frequency. A very loose way of saying it is if changes in the scale size of spacetime affect something with a real size that can't, quote, counteract the change. It's a really loose way of saying. Then the thing will be stretched or compressed with the change in spacetime. One of the central and experimentally verified tenets of special relativity and general relativity is the constancy of speed of light for all observers. When this is extended into general relativity, it gives us a null geodesic. Also, the proportionality of the frequency of light to its energy is what got Einstein the Nobel Prize, not relativity. So this is very well established too. If the speed of light does not change and the laws of physics are the same everywhere, then the same process will emit the same wavelengths of light regardless of the size scale of the universe. When that light traverses the universe between emission and observation, in order to maintain the constancy of the speed of light as the universe expands, given its energy, the wavelength must change to compensate for that expansion. Look, I'm really trying not to get too deep into the derivation of the Friedmann-Robertson-Walker metric and show the tenets of special and general relativity create the Einstein field equations, where this metric is one solution given the nature of spacetime. I'm also really glossing over the fact that the A of T contains all the physics of how the universe's contents affect the space-time. I'm trying to get the highlights of the points and dodge all the point-by-point steps that get us there. It's just that given how photons carry momentum and that their path through space-time creates a change in their momentum, ultimately means that there's a direct link between a universe with the ways space-time intervals or distances are measurements and the energy output of those photons, and the energy of those photons that take that path. Another nice but quite loose way of thinking about it is the total number of wave peaks between the source and destination doesn't change. If you look at the universe when it was smaller and stopped the expansion and let fly the photons, you could count the number of wave crests between all the endpoints. Then you expand the universe and stretch all the lengths between the source and the destination. Stop the expansion and do the same thing. The number of wave peaks would be the same. For that to happen, the wavelength goes up and the frequency goes down. The speed of light, then, being constant, means that if we see a redshift that is not due to the relative motion of the endpoints, then it is due to the stretching of space-time itself. You might be asking, well, where does all that photon energy go? The photon frequency is decreased, so it looks like there's an energy loss. But there really isn't. The universe is a totally closed system, so there isn't an increase in entropy of the photon field due to this expansion. If there were some loss of energy to the universe in some way, then the laws of thermodynamics say it would eventually go into heating something, which would then in turn eventually make more photons, because heating things up makes photons. This means that the expansion of the universe and its action on photons would somehow make the universe brighter. But this isn't seen. Quite the opposite, in fact. Another way to say this is if we ran time backward, we would return to the same photon energies as we left them. This is an underlying assumption of the universe being a closed system, not to be confused with a closed geometry. In a sense, light itself is closely tied to the measurements of the universe. We can look at the speed of light as a conversion factor between space and time. Just think of this following thing. Light travels at 186,000 miles per second. So we can say that 1 second is 186,000 miles. And that's a really good way of thinking about how we relate space and time. 1 second is 186,000 miles. Photons just happen to only travel at that one speed. Gravitational waves also travel at the speed of light, but that's a different video. So let's divide out all those lambda emits and we're left with scale factors. And then if we define A naught, A sub 0, A sub observed to be 1, meaning the scale factor today is 1, then we rearrange this equation to have something that looks insanely simple. Redshift is that the redshift and scale factor relationship. It clearly shows that if we look back in time for when the scale factor was smaller, z gets bigger as expected. For the Big Bang, when the scale factor starts to approach 0, z goes to infinity. It means the farther back in time we try to peer, the redder the light becomes. This is why I keep hammering on this point. This is why I keep saying it's an expansion. But why can't it just be everything that's really flying away from us? Why can't it just be a Doppler shift where it's just due to motion of the galaxies through space? Well, first, with all the observation we see and the many dozens more that exist, the recession to speed distance relationship does not have a dependency on the direction you're looking. It would be an astonishing coincidence if this were only due to the simple motion of galaxies. A process would have to be devised to make it so they're flying away faster and faster the farther they are from us. This just seems patently absurd on its surface. We do not observe something similar from any other galaxy, or some doubling up of speeds due to some big galaxy between us and a more distant one. No, it's a linear relationship centered on us. That just is what we see. Well, that sure does make us seem pretty darn special, doesn't it? But wait, that would mean there is some physical law here, or centered on here, that applies only to us and to no other place in the universe. You know what? Every time anyone has ever thought that in the history of science or philosophy, they've always been proven wrong. Geocentrism, dead wrong. Only planets in the galaxy, wrong. Only galaxy in the universe, wrong. Humans are the only form of life with feelings and emotions, that's wrong. Earth is the only planet on which liquid water occurred and oceans that happened that were hospitable for life, that's wrong. See also Mars. Therefore, the cosmological principle, or rather the Copernican principle, holds here too. We are not special. So we're not at some center, and we're not different from any other galaxy. An astronomer in any other galaxy in the universe would also see the same Hubble law. Anyway, this all goes by way of saying that the change in redshift directly measures the change in the scale factor size. At z of 1,000, the universe was 1,001 times smaller than it is today. At that redshift, the cosmic microwave background is a cosmic mid-infrared background. With all that in hand, let's keep moving. It's worth going over a few examples to make sure we got this down. Here we see a classic example of the stretching of a photon's wavelength as depicted on the surface of a balloon. This common picture is the result of light traveling on a null geodesic. In special relativity, we don't have any curvature, so the Minkowski metric clearly shows the speed of light's constancy. When we extend the constancy of the speed of light in curved spacetime, and specifically curved spacetime that's allowed to expand, then a photon's wavelength and frequency both change as the universe expands. I derived the whole thing in a different video where redshift comes from. Light, again, only follows null geodesics. Normal particles don't. This expansion only applies to photons and whatever else someone may think up one day as traversing null geodesics. That's why we use the balloon analogy. It's a hypersimplification which tries not to talk about the metrics and length measurements and all that, but you can see the grid on the balloon changing, and that means we're measuring lengths and times in a curved, expanding space. Some things move in particular ways in those spaces, and we have to take those into account. So, redshift arises, 1, because the photons have a constant speed of light, the universe measuring sticks are given by the Friedmann-Robertson-Walker metric, and 3, the universe is expanding. The third bit is the conclusion you must draw if you agree to the idea that C is a constant and that relativity is a thing, and that you have discovered that photons, momenta, and energy are dependent on their frequency. Since there's ample experimental evidence for all of this, we just keep walking our science along, seeing if that idea breaks anywhere, and as of today, neither idea has been broken, and not for lack of trying. So much for balloons. Now let's take a look at the observer's horizons in the expanding universe. Here what I've done is I've created a little kind of tiny universe made out of a yellow bubble. The yellow bubble will be centered on the yellow robot. There's also other robots in there, a blue one, a red one, and a purple one. Each of those represents different observers in different galaxies. So all of these objects are extremely far apart, and this just happens to be a person or observer or alien or whatever you like to call it in some very distant galaxy. Let's just see what happens if we allow for the expanding universe and see who gets to see what. Inside of yellow's capability of observing, we have the red one, the blue one, and the purple one. So now as the universe expands and everybody spreads apart, the yellow one, the blue one, and the red one, all four of them stay inside of yellow's universe, as it were. But each of these observers, because of the nature of the expansion, has their own horizon too. Notice how the diameter of the balloon, or the yellow area, expanded from that small area to this large area. If we assume that the blue robot had his small area, the same air volume as what we saw beginning of the yellow, we should actually see something a little like this. Notice for the blue observer that the red and purple robots are outside of their view. They do exist, they're just outside of his view. Likewise with the purple robot, only yellow is inside, and finally only the yellow is inside the red. So all of these outer far robot observers, or whatever they are, whoever they are, these things, they are very far away from each other, far enough that they're outside of each other's horizons. They don't mix. So we have a series of horizons that are all stacked up on top of each other, and none of them is the end. For us, let's say we're the yellow observer in the middle at this point, we have an observable horizon it's kind of indicated by one of those, the circle that surrounds the yellow observer. But that yellow observer has only that as its horizon, and that horizon is the limit of a redshift of, say, very large. If that redshift becomes larger and larger and larger, we see that it gets to a point where we have a maximum look-back time, and that maximum look-back time is the age of the universe, meaning the speed of light times the age, how far light is able to travel since the beginning of the universe from a certain point. And that's what we mean by this horizon. So That actually makes an interesting statement because blue sees the same thing, red sees the same thing, purple sees the same thing. Everybody has their own horizon. More importantly then, where do those horizons end? Because presumably to the right of the red observer, there's more observers, and to the upper left of the blue observer, there's more observers, and to the left and down from the purple observer, there's more observers. Where does that end? How does that stop? Don't know. Currently, it could just very well be that the universe is infinite in extent spatially, which is a fascinating statement. If the universe is infinite in extent spatially, then all these observers all see all the same thing, which is truly fascinating. It means we're really in no such spatial place at all. So let's take a little bit and check what exactly I meant by that previous statement of the cosmic horizon. And to that, we're going to also whack on the idea and bash on the idea of the light year as a result. So once again, let's go back to the concept that was elucidated with that little animation I did before, which is that the galaxy rushing away from us, well, it emitted light, and the light traveled along this line to get to the telescope. We saw that before. But now this is elucidated in kind of a graphic format here, where time progresses from ago at the bottom to now at the top, and we're at this galaxy that's on the left that stays put. And the apparent change of the galaxy, or the actual change of the far galaxy as it rushes away from us due to the expansion of the universe, is on the right-hand side. And the photon that travels comes from that right back over to the left. So there's an emission distance, which is the proper distance at time of emission. There's the proper distance at now, which is when the galaxy is, where the galaxy is now. And these are proper distances, which means if you simply stop the expansion and then put out a bunch of measuring sticks down now and just added those all up, that's the distance you'd have. And you could measure that in light years if you wished. But wait a second, measure in light years? Hold on. The light travel time distance is simply the speed of light times the time difference between then and now. And that's what we call the light travel distance. So people at public events always ask about, and they're told that light years of the distance to some galaxy are way over there. Even NASA uses this on their website. Oh, the light's been traveling to us for 12 billion years, or sometimes they'll just get short and say this is 11 billion light years away, or whatever. Well, light years are conceived as the speed of light times the time it took to travel from there to here. And this is absolutely not the same as the proper distance at either the time of emission or the time of observation. It's a completely different distance measurement because light travel time distance does not take into account any aspect of the expansion. There's another distance we call the co-moving distance that's often used. It is the proper distance divided by the scale factor. This means that two galaxies, if they had no random relative motion, would stay at the same co-moving distance as cosmic time progressed. Proper distance is tied to the expansion, so it changes co-moving distance as the distance removed from the scale factor. So light travel time distance really isn't anything, but it's what a lot of people think about and what they think it is to be when they hear about the distance of something, when they hear about it. Say, oh, this thing's from James Webb Space Telescope. We see the light as it was 200 million years after the Big Bang, so it's 14.7, 14.1 billion light years away or whatever. The most important thing is that this is not the same thing. We see that the distance traveled is not the same thing. Light travel distance does not take into account any aspect of expansion. It's simply a speed, which is c, times a time interval. It does not take into account anything related to the scale factor or the expansion. So that's pretty interesting. And it's also something that we kind of have to look at more carefully. So let's go back to the horizon and put it in terms of a graphical format in this way. So we're going to look at redshift. I said before in that previous thing with all the robots and balls that we were talking about redshifts and look back time and distances and horizons. So we know that if the redshift increases with time, as we look back in time, as you can see in the left-hand column, the redshift goes up and up and up and up and up. And we're looking back in time, the look-back time, all the way to the right. Notice that the redshift goes up very steeply towards the bottom, and the look-back time starts to level off and change not at all. And in fact, past a certain redshift, we have zero change in look-back time. That's because redshift measures the expansion rate of the universe from the time of the Big Bang. And the Big Bang is roughly 13.7 billion years old. Now, this set of numbers came from the fact that we assumed a flat universe with h naught equals 71 kilometers per second per megaparsec with a standard lambda CDM cosmology. Then we can derive all these things for a given redshift. And notice that maximum look-back time of 13.7 billion years. And there might be a lot of confusion because if you look just to the left of it, the present distance is 47 billion light years. It just sounds like they're completely different distances. So which one's the correct distance? And one seems way too far away. I mean, the universe is only 13.7 billion years old, so how can something be 47.5 billion light years away? Again, that's the expansion of the universe, and the present distance is a proper distance, the proper distance today, right now, if we stop the expansion and just lay down a bunch of markers. That fourth column, we use units of millions of light years. We see that instead of megaparsecs are a geometric measurement, which is measured based off of trigonometry based, ultimately off of the angular change of a star in the sky due to the Earth's motion around the sun. That's where the parsec is defined. So it's very, very geometrically based. But light years is just a distance times a time. Well, a distance divided by a time, or a rate, a speed, a known speed, or an established speed times a time interval. It's not a geometric distance. So everyone learns that a light year is just the distance light travels in a year, and that is completely true. However, the implication of that statement is that all distances are the same, and that a distance is a distance is a distance. One is just different units from the other. Our memory and our cultural bias say that if something's 10.8 billion light years away, then it emitted that light 10 billion years ago. More frequently, in more responsible places, people will just say it emitted the light 10.8 billion years ago. But they won't say that it's 10.8 billion light years away. They'll say it emitted light when it was 10.8 billion years ago. So if we want to say 10.8 billion years ago it emitted light, and it's 10.8 billion light years away, that's not true. In an expanding universe, something that's measured to be 10.8 billion light years away emitted its light only 7.7 billion years ago. Now we're getting confused only because we got attached to this idea of light speed as a unit of speed in a high school physics sort of way, where distance equals speed times a time, and the fact that all of our experiences with non-curved, non-expanding spacetimes. We're just hung up what we learned in grade school and high school because light years sound really cool, and it's very easy for the teachers to teach, especially when you say distance equals speed times time. It makes it kind of fun for them to teach. But the idea or intuition or common sense that we have from that early idea breaks down when we discover the evidence for an expanding universe. Another way to view this horizon concept is with this graph. When we think of a time horizon, because as we saw in that graph before, there was definitively a look-back time maximum. Redshift went up to infinity, but the look-back time had a maximum time of 13.7 billion years ago. So we can look at that as a time horizon from which we cannot see any time before. In every direction, if we look farther and farther away, objects we look at are deeper back in time. If we look far enough, quote, we get to the Big Bang, but all of its light would have been redshifted down to impossible to detect wavelengths. More interestingly, we can see that there's a maximum proper distance for this emission, and that can be seen by this graph, which shows that it's somewhere around 5 gigaparsecs, or if you really want to go back, 15 billion light years. Farther out than that, and make mostly farther back in time, the size of the universe in cosmic history was actually much smaller, and that the emission distance starts to be comparable to local distances and gets closer and closer, and eventually gets very close to zero, or at least down to the size of some primeval fireball that would eventually make up the universe. And that happens, of course, at the Big Bang. The outer ring of this graph, this green ring, is the emission distance of almost zero. I mean, this sounds bad, but it does work out. It works out due to at what point in cosmic time do you want to start your emission process and send the photon on its merry way? Again, if the volume of space is really small and you are right around the beginning of the expansion and you throw a photon at a target, the expansion quickly drags it away, like a very fast escalator with a kid running the opposite direction. The kid keeps running at the same speed and covers a lot of distance, but the distance keeps growing underneath him. At each moment, it seems like the kid is being carried further and further away, which is true, but the escalator is going ultimately at a slower rate than the kid runs. At some point, the kid gets past a point where the dragging away is less than the going forward. He'll advance slowly, then faster and faster, until the time when the target finally receives the photon, or he gets the other end of the escalator. This process for the universe is maximized for a volume of space centered on the target, of course, with the source photons being just inside the light travel time horizon at the time of the Big Bang. This is not the edge of the universe, as we saw with the example with the observers and robots and balls before. This is not the edge. This is just our edge of capability of seeing. This is our horizon, but it doesn't mean it's the edge of the universe. There is no edge to the universe. It doesn't exist. There is more stuff of the same just a little bit away outside of that horizon. And as we saw from the picture below, the three robots that were inside the yellow ball at the beginning are outside of each other's balls. So each one of them has their own horizon centered just like this. And the farther away they are, the more the space will expand, and the space will expand such that the other observers will not see each other. So there's more of the same past this horizon, and everybody sees the same horizon. But it's important to remember, we're not at the center of the expansion. We're only at the center of our light horizon, defined by the places from which light has had a chance to get to us. So that's what this graph means. We see on here the redshift increasing on that right-hand side, going all the way out to very large, where look-back time gets larger and larger and larger, and redshift gets even larger and larger. But the look-back time is a constant, sort of a steady look-back time, because that's just an advancement of a clock. And so the thing going up to like 1 o'clock or noon, we have an emission distance, and then we have an event distance as well. So these emission distances and current distance are interesting. On the left-hand side, emission distance goes up and up and up until it gets to about 5.7 gigalight years, and then it goes down to 1 at the other end. So there's a maximum emission distance from which you get the largest possible distance between the emission of the photon and the observer and the receiving. And that's just because of the nature of the expansion of the universe. And the current distance is larger and larger, getting past that 5.7 billion light year emission distance. The current distance is the current proper distance. The emission distance is the proper distance at time of emission. See, that's where we get those things from. That's exactly what those previous slides were. Proper distance at time of emission, proper distance now. That's what those two things mean. And so the other things that the going down into the left at about 7 o'clock shows the extent of the Sloan Digital Sky Survey, the Hubble Deep Field, and the cosmic microwave background, as well as when the first stars were born, young galaxies and old galaxies in the dark ages when there was no light in the universe. And those funny lines just show you that when we wish to map the points of look-back time. When was the emission distance? What was the emission distance at said look-back time? And what is the current co-moving distance right now? The current proper distance. And that's where we get those things from. Notice that the emission distance goes up from the beginning time and then swings back down and goes smaller. But then the current co-moving distance is the current proper distance, and that goes out and out and out and out and out and gets larger and larger as the universe expands. So the bottom thing is a true expression of where things are now, but the top thing is where things were ago. All right, so now that's all interesting and everything, but our original question was the measurement of the Hubble constant and the Hubble parameter and what Edwin Hubble did using Leavitt's information and Slipher's techniques. Nowadays, there are a lot of things to work out with H0. We saw well before that H0 seemed to be centered around 72. But the recent years have discovered a tension in the measurements between the Hubble constant. And you can see from this graph there are two bands, one going down the red side on the right and one going down the green side on the left. And they're separated roughly by this group of things that are direct measurements and groups of things that are indirect measurements. So let's look at each and what the impact is. First, let's look at the indirect measurements, which we didn't really talk about in this discussion. The indirect measurements come from trying to fit the Hubble parameter at the present day with measurements of the cosmic microwave background using the Planck Observatory, as well as using the same data without the Planck Observatory, and then with not using the cosmic microwave background, but only Big Bang nucleosynthesis arguments, as well as microwave lensing and power spectrum with microwave lensing. That's what those things are. Those are indirect measurements. They don't directly measure it. They're fitted curves to data. Notice that they center roughly around 67 or 69 or so. More like 67.25 or 67.3 kilometers per second per megaparsec. And that's what we see in the third one on Agamemnon 2020 with the Planck 2018 data. It's roughly 67.27 kilometers per second per megaparsec. And the error bars, that's what those things going to the left and right are, shows how confident they are in those values that they have. So now those are indirect measurements. But if we now look at the direct measurements, which are below, first we have the Cepheids, which we talked about extensively. And the Cepheid variables seem to center roughly around 73.2 or 73 or so, somewhere around 73. And then we can see that there's type 1 supernova or tip of the red giant branch groups, that's in the green, that's below. And they're a little bit lower, but they're still in agreement with the direct measurements. And if we scroll down and see other things, different kinds of standard candles, such as Mira's, Mazar's, the Tully-Fisher relation, surface brightness fluctuations, type 2 supernovae, the brightest H2 region in galaxies, and lensing related and mass model dependent lensing models, meaning gravitational lensing of objects. We see that these direct measurements of H0 lead us to roughly somewhere, with the most optimistic average is roughly 73 kilometers per second per megaparsec. Those are direct measurements where we don't have to infer anything. We have a standard candle of some sort and then some way of measuring a statistical set of standard candles versus the statistical set of the recession velocities. So there's a statistical grouping of these things for individual sources, and then when you group them all together, you get a fitted curve, just like we saw with Hubble's original curve and all the other lines that we saw in the previous graphs. This is interesting. Oh, and the bottom is a very interesting thing coming up very recently is gravitational wave detections. Gravitational waves also travel along null geodesics. So how they can do a direct measurement. Now they're not as accurate because there's only a few gravitational wave observatories and their ability to pinpoint things in the sky is very low. So that has a great impact on what their measurement is for H0. All this means there's a lot to work out with the Hubble constant. And the Hubble tension means that there are recent measurements that indicate it's roughly 68. I'll call it 67.6, we'll call it 68. And then higher values, roughly around 73 or 74, which I list the 74 one from March 18, but it's roughly around 73 is the average for the direct ones, as you can see from the red bar. And the green bar, the indirect measurements, that principally come from the cosmic microwave background or physics arguments from the Big Bang nucleosynthesis. Those two sets of measurements, all of these sets, both the direct and indirect, are extraordinarily rigorous. They're extraordinarily well understood. All sets are considered valid measurements of the Hubble parameter, but they differ. And they differ on a 4 sigma level. And what that means is that it's a very difficult thing to think that these things are actually non-significant. Like these changes, like, oh, it's something in between, and maybe it'll be just the average of these things. No, they are measuring very different qualities of something. So there has to be a relationship that tells us why one of these, why we get this Hubble parameter when we measure direct, and why we get this Hubble parameter when we measure these indirect things. There must be some reason. We don't know what it is. This is very important because it means what is the actual expansion rate? It doesn't seem like there's any systematic errors. The errors that are involved with this are most certainly embedded somewhere in here, and we see the error bars for each of these measurements. But the important part about this whole thing is we have one group of measurements saying one thing and one group another. There must be some physics or some understanding that we do not yet know that links them together or says, but if we take this into account, then they balance out or they come to this value or something. Nobody knows what that is. That is a current area of extraordinarily active research. I did a little video on an attempted kind of thing where somebody said, oh, what if light gets tired and loses energy, or the physical constants of the universe change as time goes on? There's a lot of reasons why that can't happen, and those are extensively discussed in much of the literature, and it's currently ongoing. But that was just one very flashy thing that came up in previous months. So what we're looking at is, importantly, two different tensions, this tension that is currently active research. However, just because there is this tension, it does not invalidate the expansion. The expansion does exist. It just means we don't know everything yet. That's all it means. So in the end, which version will win? The direct measurements, such as those of the Hubble Deep Field that we see on the left, or indirect observations such as the Planck, plus is interpreting statistically the cosmic microwave background of the as seen here in the Planck on the right, by the Planck telescope on the right. Which one is win? Which will win? Which one? We don't know. There'll probably be some modification of both understandings, some modification of both. So now let's go all the way back to the beginning. The cosmological principle. We look like we're at the center, but that's what every other observer will see too. No matter where in the universe we are, we will measure the same relation between the recessional velocity and the distance, the same Hubble parameter. If that's what we see, and everyone else sees it, then it's a universal property. That's isotropy and homogeneity. The universe is expanding. Now then, where was the Big Bang? We think that. It's like, oh, if it's expanding from some point. So where is that point? If we take the expansion backward in time, all the galaxies seem to originate from a single event in space-time called the Big Bang. Even though it seems like it, we must not be at that center, because every observer also sees themselves at the center. It doesn't matter which of these galaxies we see in this image. And any galaxy, any observer anywhere in the entire observable universe, they would all see themselves at the center. There is no place where things are actively dumping out or spreading away from the one place. There is no shock wave. There is no expansion front from some long ago explosion or detonation. There is no single spot that has a bunch of smoking embers or tangled up space-time or wibbly-wobbly messed up thing from which everything flowed. There really is no special space in the universe. Therefore, the Big Bang was everywhere all at once. This is due to the combination of the cosmological principle that we've discovered about the nature of the universe, and by observation, what photons are and how they carry the energy and momentum, and how we've played around with the field equations to give us something that kind of looks like a good idea. All these things come together to give this startling, inescapable, counterintuitive result that defies common sense. The Big Bang was everywhere all at once. That's pretty cool. The universe today, then, is a low-density, dark, and rather cool place. We see that it continues to expand. The universe 13.7 billion years ago was smaller, denser, and hotter. The universe was opaque and filled with radiation in the form of photons. How far back into the universe's past can we go? Go check out my videos on cosmology to learn more about that. And don't forget to subscribe and like this video. Thanks.